So I want to continue a little bit with acids and bases. I'll talk about this water dissociation constant. So water, it can act as like acid or base. And so if I have water in solution, what happens is one of these is going to act as an acid, and the other, and one thing about it, very, very tiny amount does it. Most of the water stays together. And so what happens is it's going to donate an H plus. So this acts as acid, this acts as a base. And notice I got the equilibrium, which is a very small amount. I'm going to add an H3O plus aqueous plus hydroxide ion. So in this case now, this is going to be the conjugate acid. This is the conjugate base. So again, be able to recognize conjugate acid, conjugate base. I can write this as an equilibrium expression. I'm going to call it KW. And so KW, what I'm going to do is, it's going to be the concentration of hydronium ion times the concentration of hydroxide ions. Again, this is hydroxide. And this is hydronium. And so this concentration together in solution is going to equal to this value of KW, which is 1 times 10 to the minus 14. So this is actually going to be important. And this always occurs in water. I have aqueous solution, concentration of hydronium times the concentration of hydroxide is 1 times 10 to the minus 14. Again, this is a very small amount. So you get a very, very small amount of water that actually forms an acid and a base. So a couple of things about this one. I can make this into a log value. So I can say that pH, and when I say H is actually the log of H3O plus, so sometimes we use the same thing, is minus log of H3O plus. I can do POH. Minus log of the hydroxide ion concentration. Again, normally we use molarity for this. If I combine this together, so if I take the log of the hydronium, hydroxide, and a log of this, again, log is base 10, I end up with this equation right here. So pH is equal to 14. So all three of these are actually important. But when you see that P is just a negative log of that concentration, this equation is important. So pH plus POH is equal to 14. So there's a few things, because we need to make sure we get this right. The pH is less than 7, it's going to be acidic. pH equal to 7, it's neutral. So again, distilled water is a good example. If pH is greater than 7, it's going to be basic. So we can look at the pH of a solution to determine acidic, basic, or neutral. Now, there's one more thing I want to do with this. A couple of things with this in terms of concentration. If the concentration of H3O plus, so basically, if it's acidic, that means that the concentration, the molarity, is greater than 1 times 10 to the minus 7. When it's greater than 1 times 10 to the minus 7, it'd be on the order of like times 10 to the minus 6, 10 to the minus 5, etc. When something is neutral, H3O plus concentration is equal to 1 times 10 to the minus 7. If it's greater than this, greater than 7, that means that the concentration of H3O plus is less than 1 times 10 to the minus 7. So again, these are some values I want us to know. One more way to write this is that this case, what this means, if it's acidic, the concentration of a hydronium ion is greater than that of hydroxide. Neutral, they're the same. If it's basic, H3O plus its concentration is less than that of the hydroxide ion.